Hello, good evening, guys. So, are you able to hear me and see my screen?
Very good evening, sir. Yeah, it is visible, sir.
Okay, good. So, I'm just recovering from a bout of fever and throat infection. So, if my voice is a little low or if you want me to repeat anything, you can tell me, okay? So,
Okay, sir. Thank you.
thank you. We'll just wait for 2 minutes and then we'll start. Okay, so we will start. Um, Good evening, everyone, once again. So, I'm Nand Kishore from the Department of Electrical Engineering, IIT Delhi. So I'm pursuing my PhD under the supervision of Professor Somesh Pranag and Sumit Kumar Pramanik. So just to give some background information about myself, so I am working on gallium nitride devices. Some of you may have heard about them. So similar to how you have semiconductor technologies based on silicon, nowadays people are rapidly moving towards silicon carbide, and gallium nitride is another new addition to that. So the advantage you get with these devices is, of course, you aim to go towards ideal switches, right? So this is actually a step towards that direction. We will be seeing that in this course as well. You would have covered it during the normal lecture hours. But anyway, I'm working on that. That's about my topic. So today is, we are supposed to do the problem solving sessions, but this week it was mostly kind of a theoretical concept that was covered in the NPTEL lectures. So in alignment with that, we will be seeing a number of multiple choice examples wherein you will be applying what you learned in this week to solve these questions, and these may be helpful towards solving your weekly assignments as well. So from the next week onwards, we will be solving more numerical kind of questions, but today it will be mostly theoretical. If we get time, I actually have prepared some numerical questions. If we get time, we can go ahead and discuss that as well. They are just kind of extra, so they may not be entirely useful for us as far as this week is concerned. But anyway, we can go ahead and discuss that if we find time. But first, we will try to cover up the theoretical portions. So I guess I have started recording. Yeah. Okay. Yeah. So in this week you had your introductory lecture on power electronics. So why we use them. I guess all of you may be well aware of that by right now, since you have enrolled in this course. And then electronic switches were covered. So as you know, switches can be categorized into three, right? So one is diode, that is totally an uncontrolled device, and transistors and then thyristors. So why do we have these three classifications? Is many of you may be aware, it depends on the number of PN junctions, right? So diode, as you may be aware, is only a two junction device. That is, it has only a P and an N junction. Of course, you may tell that you add a drift layer to increase the voltage blocking capability. But anyway, it's an additional layer. Anyway, primarily it's a two junction device, right? Transistors have three junctions, right? So you take your NPN or PNP BJTs, or you have MOSFETs. So all of these are three junction devices. And finally, you have the SCRs, or I mean thyristors. So thyristors is a large class of family in which the number of junctions is four or more. So any device that has four or more junctions, you categorize that as thyristor. Okay, so in that you can have triac, you can have your diac, you can have your excuse me, you can have GTOs, you can have ACRs, right, and so on and so forth. So anything that has four or more layers in that. Okay, that's the exact term, layers. So number of physical layers or the physical stack up you have. So that defines the category in which the device is going to come, whether it's a transistor or thyristor or a diode. Okay. So these can also be categorized based on their controllability. As you know, they can be uncontrolled or semi-controlled or fully controlled, right? Uncontrolled, as you all may be aware, is a diode. Semi-controlled device is your SCR, and your fully controlled device can be your BJTs or MOSFETs or whatever. I mean, you have conduction during its turn on and turn off, right? So that is the I mean, that's the criteria based on which we categorize the devices, right? Okay, so once you saw that, I think you also had some discussions on device physics, though that's not entirely applicable for us. We just need to know about what's just going on inside that so that we get an overall bird's eye view, right? And then you also got to know about the operation and the VA characteristics of these examples of these, that is a diode, thyristor, and GTO. And as I told, the reason these three devices were covered in your lectures was diode is uncontrolled and thyristor, or I mean SCR is a semi-controlled device and G2 is a fully controlled device. Correct? So this was what was covered in the previous or prior lectures. So today we will be doing the problem solving session based on this. I mean, not exactly problems. As I told, there will be multiple choice questions. And at any point, please feel free to stop me, and if you have any doubts, you can raise your queries as well. Okay. And if by any chance I get logged out due to network issues, I will be logging in from another device. So kindly bear with me in case it takes 5 to 10 minutes. Okay. 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 So this is just a table summarizing the devices and their operating quadrants. And of course, the device symbols, you may be experts in that by now. But anyway, so as you know, for example, this diode, it is capable of conducting current, right, unidirectionally, and it is also capable of blocking opposite voltage. I mean, voltage of opposite polarity, right? So that's the reason it is said to operate in the second quadrant, right? So yeah, right. So this is something you all are pretty aware of, and you have your BJTs, which can again conduct current in one direction. That is, you will have your collector current or emitter current, which always flows in a particular direction. It cannot have dual polarities of current, and of course, it is capable of blocking only one voltage, right? Only unidirectional voltage. Okay. And we will come to FET over here. That is your MOSFET. It can be an N-channel MOSFET or P-channel MOSFET, doesn't matter. But the point is, it can block voltage only in one direction. Why is that so? The reason being that you have an anti-parallel diode connected across its drain to source channels. You may be aware that this is your drain and this is your source. You have an anti-parallel diode, and diode, as you know, is an uncontrolled device. Therefore, what the diode cannot do is block positive voltage, correct? So positive voltage for this diode means source is more positive, I mean, than the drain, correct? So if your source is more positive than the drain, then this diode is going to conduct, which means that it can have bidirectional current capability, but it cannot have bidirectional voltage capability, right? So if your gate bias voltage is positive, that is if your VGS is positive or above the threshold, then you know that it's the drain channel is going to get formed or the drain channel is going to start conducting, right? If your VGS is going to exceed your threshold voltage. So you know, you are very well aware that it can have ID conduction in this direction from drain to source. Because of this diode, it can have conduction, that is current conduction from source to drain because of this diode. And also it can have unidirectional voltage blocking capability, right? Because if you apply a positive voltage from drain to source and you make sure that your gate voltage is less than your threshold voltage, then this drain channel is not going to conduct no matter what. Correct. So you can understand that it has bidirectional current capability, but only unidirectional voltage capability, right? And then you have your GTOs. Okay. So I have not included your ACR over here. You may be aware of ACR as well, but anyway, GTOs are similar to that, in which it can have current conduction in a single direction, right? That is from anode to cathode, right? But it can block voltage in both directions. Correct. I mean, you may be aware of its operation and stuff, but anyway, I just thought it's good to mention over here. Therefore, you have bidirectional voltage blocking capability, but only unidirectional current conduction capability. Correct. It can conduct only from anode to cathode. Okay. And you have other categories of, other criteria for categorizing these as well based on the carriers. That is, you have minority and majority carriers. So over here, you may be aware that diode, conventionally diode is a minority carrier device, and your GTO is ACS, all of these are minority carriers, whereas your FIT happens to a majority carrier device. Okay. So all of these are some categories of devices that you may be already aware of, but what we aim to do as we have rapid advances in the field of power electronics, one of the main thrusts is in focus of this, realizing an ideal switch. Is it possible to get a switch that can do all things, right? You have control over its voltage blocking capability and current conduction capability, right? So this is what we want, ideally. So does anybody know of any switch that can provide all of these? Um, you may be aware of a device called TRIAC, right? Bidirectional triode thyristor, and it is supposed to be capable of bidirectional current conduction as well as bidirectional voltage blocking. Okay, so it is used for AC applications. That is AC to AC conversion applications. Okay, so TRIAC is a switch that's used for that. Anyway, we will be going in detail when we cover AC converters. But anyway, as I told, this is what we aim, right? That is, we want a fully bidirectional switch. Even over here, uh, these are idealized VA characteristic. I mean, it necessarily does not mean that your VA characteristic are going to be something like this. For example, your MOSFET VA characteristics may not be something like this. It will never be something like this. Of course, you are going to have forward voltage drops, and then you are going to have your channel resistance and other non-idealities. But anyway, this is the ideal characteristic you look for, right? That is, it should be able to conduct current without any drop, right? And it should be able to block voltage without any leakage current. So these are some characteristics of ideal devices that you may, of course, be aware of, right? So if you don't have any doubt, we can go ahead and jump on to problem solving. Okay. Okay. So this is something that you may be well aware of. So MOSFET is which type of device? Current control current or current control voltage control voltage device, or voltage control current device. Okay. So, but anyway, before we proceed with this, in networks, you may have covered four types of sources, right? So if you talk about sources, just a second. Okay. So if you talk about sources, you may be well aware that you can have dependent as well as independent sources. correct? So independent sources, you can have a proper voltage source or a proper current source. Okay. So, and the representation is something like this, correct? As far as dependent sources are concerned, you have four categories. That is something called as VCVS, which translates to voltage controlled voltage source. You have something called VCCS, and then you have CC. I mean, you have CCVS, and then you have CCCS. Correct? So you can categorize any switch, or for that matter, any analog device as one among these. That is, it can be a voltage controlled voltage source. Okay. For example, your op amp, you may be well aware that op amp is actually a voltage controlled voltage source. Okay. So any analog circuit that you make, that can be categorized among these. Okay. It can be dependent or independent, and if it's dependent, it can be either of these. Okay. So in that same radar, what is MOSFET? That's the question, right? So if you actually go to the uh, normal working of a MOSFET, you may be well aware of that anyway, but still, right? So this is the conventional symbol that you use for a MOSFET. Some people also prefer something like this. Okay, so please note that this is something that analog people use. That is, this represents generally is used. This representation is generally used for low power. Okay, and this is generally used for high power. Why I am emphasizing this high power MOSFET is one thing is you will be heavily dependent on this diode for some period of operation. As you go ahead, you may encounter something called as a dead time in the operation of converters. Okay, so during that period, you expect this diode to actually conduct. Okay. However, for low power applications, I mean, even the application and the topology may be different, but over there, you don't need this. You're not heavily dependent on this diode, one. And second thing, is over here the rating of the MOSFET is quite low. Okay, it may be maximum 3 volts or max to max 5 volts that you use for computer applications, and mostly these are used by analog people who deal with 6 nanometer MOSFETs. People manufacture 9 nanometer MOSFETs and stuff. But anyway, that's outside our domain. Our domain is in high power, right? So wherein you expect the MOSFET to block 1.2 kVs, right? 1.2 kVs and conduct some 60 amps of current and something like that. This is a typical rating of a MOSFET. Okay. Okay. So now that we got this, so what really happens over here is okay. So I will just get rid of this. Okay. So um, so I'm drawing a typical application circuit of a MOSFET. Okay. So in order to do your VA characteristic, what you do is something like this, right? So you apply a known value of VDS, maybe around 10 volts, okay? Maybe around 10 volts, and you also have your VGS, okay? You have something called as an RG or a gate resistance, okay? And you see what is your ID, okay? What is your ID for a particular value of VGS? So from this, you may be able to guess that you're controlling your VGS value, and you see what's your drain current or the channel current, right? So effectively we call this as drain current, but effectively what's happening is there is actually a channel that's getting formed over here across the drain and source, correct? We call this a side channel. So as you vary your VGS, your I channel also varies, correct? So from this, you can actually guess that VGS is your input and I channel is a consequence of VGS. Therefore, you can tell that it's a voltage controlled current device. Correct? Also, you can also verify it from the VA characteristics that you draw. right? So what you get is something like this, correct? Okay, it's not according to scale, but anyway. So this is for increasing value of VGS. So what happens over here is as your VGS increases, you see that your current also increases, right? Why does this happen? Um, you may be aware of the regions of operation. You have something called as the cutoff region, correct? And then you have something called as the ohmic region, correct? Wherein you have a constant slope, and the slope is actually RDS on. Okay, this is your RDS on or your R channel resistance. That's what we were telling, that ideally your channel resistance needs to be zero, but anyway you don't see an ideal RDS, right? I mean an RDS of zero anyway. And then you have your saturation region. So what happens is your channel current, or I channel as you call it is given by, this is actually an extra information, but I think it would be really useful for you guys to know, right? Your channel current is actually given by GM times VGS minus VTH. So GM is your trans conductance or the channel conduction parameter. Okay. So they call this as the trans conductance. So this is entirely dependent on the material characteristic, right? Okay. So it depends on the, as they say, the length of the channel, the width of the channel and stuff. Okay. So this is your transconductance. Then this is your VGS that you apply over here. And this is your threshold voltage, V threshold. So now you can understand that why if you increase your VGS, this is also increasing, correct? So it is actually following this particular equation. Okay. And again, from this equation also, you can observe that you vary your VGS and your I channel varies. Therefore, it's a voltage controlled current source or voltage controlled current device. Okay. So this is just some extra information, but anyway, you now know that MOSFET is a voltage controlled current device. Okay. So voltage, this is a MOSFET and op amp, for example, is a voltage controlled voltage source. And what else? Your BJT is a current control current source. Why? Because in BJTs, you have your IB, which is going to control your IC and IE, right? Correct? So over here, so over here, you of course know that by KCL, I'm sorry, IE is equal to IB plus IC, right? So this is one equation. And anyway, you also know that your IC by IB is your amplification factor, or it's called the current gain, beta, right? So you vary IB, your IC varies by beta times IB, correct? So generally beta can be around 10 for power BJTs. For analog BJTs, you may have studied beta values up to 100, correct? However, for power BJTs, the beta value is a little lesser, okay? So you have beta as 10. So 10 times IB will be your IC. So you understand that you vary IB and your IC varies. So your IC varies, IE also varies, correct? So this is why we call BJT as a current control current source. Okay. So these are just some examples of other devices, but anyway, this is the answer to this question. So next we go to this. As compared to PN junction diodes, Schottky diodes have dash. Okay, so low operating frequency, low reverse leakage current. Okay, so the question is about what is the frequency and what is the leakage current. Okay. Okay, so one thing is ideally you want a switch to be operatable, to be operable even at DC, correct? You want the frequency range to be from DC till tens of megahertz or infinite megahertz, correct? Tens of megahertz, hundreds of megahertz. This is what you want ideally. But practically, this is not possible. Okay. So you will see that the range of operation of your device is actually restricted to few kilohertz or max to max few megahertz, nothing more than that. Okay. So why is high frequency desirable? You will learn later that as you go for high frequencies, the size of your converter or the size of your passive elements, that is your L and C. Passive elements are basically your inductors and capacitors in any converter. They will reduce as you go for higher frequencies. So F increases, LC values will decrease. Okay. So if your LC values decrease, the size of LNC will also decrease. So due to which your converter will become power dense and it will become compact and stuff like that. So we want to go for higher frequencies. That's one thing. But however, practically speaking, we cannot go towards that. Right? Why? One thing is, okay, let's say a device is turning on. So when a device turns on, what happens? So prior to device turn on, I mean, okay. So prior to device turn on, the device, God, the device was blocking voltage. Okay. So it would have been blocking, let's say 600 volts, and it was having zero current in it. Okay. This is before turn on. So after turn on, what you want is the device to carry, let's say 10 amperes, and the voltage across the device, you expect it to fall to zero. Correct? And you want this to happen instantaneously, right? So before, let's say at this point, I'm turning the device on, which means that the voltage you want it to fall from 600 to zero, correct? And at the same time, you want your current to increase from 0 to 10. Okay. So this is 10 amperes and this is 600 volts. Okay. But ideally, this is something that's impossible. Okay. So what you will actually see is something like the voltage takes a bit of a time to fall, right? And the current takes some time to rise. Okay. So you have some time that's going on over here. I will call this as T on. That is the turn on time period. Okay. So now from this, you can understand that this turn on can be for different devices. This T on is different. It can be a few nanoseconds. Okay. Or it can be up to a few microseconds, 5 microseconds, 10 microseconds is even possible. So you can understand that if your turn on time is 5 microseconds, and let's say your turn off time is also 5 microseconds, it means that the device takes 5 microseconds to turn on at all. I mean, it takes 5 microseconds to even turn on, right? So it means that you cannot go on increasing your frequency because there is a time delay over here of 5 microseconds or 10 microseconds, whatever. Correct. So this is one thing. So this is the reason you cannot go on increasing your frequency. Okay. And of course, you will be aware of what's the leakage current. That is when the device is blocking some voltage, you don't want any current in the reverse direction. Correct. So whatever current is flowing in the reverse direction, it may be of the order of microamps or nanoamps, but you don't want any of that, right? But you may be aware that a diode has some leakage current, right? It has some leakage current through it. That's basically due to the carriers inside the device, right? But anyway, you want this to be as low as possible. So the question over here is, as compared to the conventional PN diodes, Schottky diodes have what? So one thing is, of course, in a PN junction diode, you have your um, P doped region and N-doped region, you will have your barrier over here. But in a Schottky, what you have is you have a metal contact, right? So metal contact. So it's not necessarily a semiconductor doping, right? You have a metal contact and then an N region, correct? So this metal contact actually facilitates a larger leakage current. Why? Metal contact is a pure conductor, right? Unlike a semiconductor, it's a pure conductor, which means that it doesn't have any what you call as the barrier potential between your valence band and conduction band is lesser in a conductor, right? I mean, it doesn't have any distinction between your valence band and conduction band. Both will overlap actually, right? Because of that, it's easier for the metal contact to conduct current, which means that it will have a higher reverse leakage current. So it can be either this, okay. Okay, so you have only one option over here. So this is the answer, right? High reverse leakage current it will have because of what? Because of the metal contact. And also it can operate at a higher frequency. Why? So there is a reason for that as well. Okay. So one thing I told that it is restricted by T on, correct? There is also another thing that happens during the turn off of a diode. Okay. So during turn off of a diode, you may be aware that there is something called reverse recovery, correct? It means that the current does not fall to zero and stay at zero, right? It will fall to zero and then it will go negative, correct? And after that, it takes a finite amount of time to come back to zero. Okay, so this is what you call as a reverse recovery. Correct. So this is what you call as reverse recovery, and I will name this as IRR, reverse recovery current, and there is a particular TRR. Okay, and you may be aware that this reverse recovery is entirely due to the PN junction, right? It is due to the recombination of the minority carriers in the PN junction. So this um, if you have your P and N junctions, both of them semiconductors, you're going to have a very large reverse leakage, reverse recovery current. However, if you have a Schottky diode, that is, you have a metal contact, it means that the reverse recovery current is going to be way lesser. Okay. Okay. So because of that, if your reverse recovery current is lesser, it may not take this much time to actually come back to zero. If your current is lesser, obviously it will come back to zero faster, right? Okay, so the TRR will be lesser. So TRR is lesser for Schottky diodes. Okay, if your TRR is lesser, it means that your turn off time, the time taken for the device to actually turn off or the current to actually reach zero is lesser. The T off is lesser. Okay, if your T off is lesser, it means that I can increase my switching frequency. Correct? So this is the answer for this question. Okay, it can Schottky diodes are generally used for high operating frequencies. However, they have a higher reverse leakage current, but if that's acceptable for your application, you can actually use Schottky diodes and operate it at a higher frequency. And as I told, at higher frequency, you get advantages such as reduction in the converter component size and stuff. Okay, so we'll go to the next. Okay. So one of the differences between diode and triac is okay. So basically it's about the control, right? So one thing is diode is what? Diode is, before we even go into the examples, you will be aware that diode is totally uncontrolled, correct? You apply a positive voltage, it will start conducting, right? No matter what. And anyway, we generally have a cutoff voltage or a cutoff voltage of around 0.7 volts, but anyway, for practical purposes, we can go ahead and neglect it. Okay. So we have points on volts over here. Okay. So obviously these two options are eliminated. They don't have a control turn on. And track is what? Track, as you may be aware, is actually two ACRs connected in anti-parallel, correct? So you get a bidirectional voltage blocking and bidirectional current conduction. Okay. So and of course, diode does not need gate pulse to turn on as well. So this is the option. Diode has unidirectional current flow, which I'm sure all of you agree with, right? Right? And triac has bidirectional current flow. As I told, it has two ACRs in antiparallel, due to which if you turn, if you forward bias one of the triacs, if you actually draw it, correct? I will call this anode and this is cathode, right? If I forward bias this triac, I can have current conduction from anode to cathode. And if I forward bias this ACR, I can have current conduction from cathode to anode, correct? So triac has bidirectional current flow, which is true, and diode has unidirectional current flow, which is also true. One more extra piece of information. So how do you represent this current? Correct. So the diode current is generally given by ID is equal to, this is an empirical formula. It's also called Shockley's equation. So ID is equal to IS into VD by eta VT minus 1. Okay. So this is the diode current ID. Okay. And let me call the voltage as VD. So what is IS? It is your reverse saturation current. It will be very, very small, of the order of nanoamperes or even lesser, right? And uh, eta is something called as emission coefficient. So this is going into device physics a little, so I'm not going into derivation of these things. And VT is called thermal equivalent voltage. Okay. So Vt is further given as Kt by Q. Of course, it's not required at all, but anyway, K is your Boltzmann constant. Okay. And T is the temperature in Kelvin. Okay. And Q is the charge of 1 electron. Okay. Anyway, this is not required, and generally, numerical questions based on these, they will be giving you what is VD, ID, and eta, everything. I mean, VT turns out to be around 26 millivolts. They may give this. Anyway, this is 26 millivolts at room temperature. At different temperatures, it will vary because it has this coefficient of T. VT is directly proportional to temperature. So based on this, you can calculate your diode current. So from this equation, one more interesting thing that comes out is that based on your temperature, VT is going to vary, and because your VT varies, your ID also varies, which means that your diode conduction is heavily dependent on temperature. Okay. Anyway, this is not required for this question. Anyway. Okay. So AC motor behaves like which type of filter? You have different types of filters, right? Low pass, high pass, band pass, and band reject filters, notch filters, and stuff, right? So before we go into this problem, you have your low pass filter, which means that at lower frequencies, it's the impedance is going to be very low at low frequencies, right? And at higher frequencies, impedance is going to increase, correct? So in the impedance curve, what do you expect to see? In the impedance curve is impedance will be very low and then it will go on increasing at higher frequencies, right? So this is something you expect in a low pass filter. Okay, it may not be exactly like this. You have multiple things, like it may be like this or something like that, but anyway, you get the point, right? With the same vein, you can plot what is your high pass filter. In a high pass filter, what happens is um, at higher frequencies, your impedance is going to be low. At higher frequencies, and at lower frequencies, your impedance is going to be high. Okay. So your impedance will be high at low frequencies, and as your frequency increases, your impedance is going to fall. Pardon me. This is log F, and this is also log F. Got it? Similarly, you have your band pass filter. So wherein your impedance frequency, I mean your impedance characteristic will be something like, okay, at I mean, it will allow the signal to pass only in a certain range of frequencies, okay, between Z minimum to, sorry, F minimum to F maximum, correct? Which means that the impedance will be low between these frequencies and then it will again increase at higher frequencies, okay? So this is F minimum and this is F maximum, okay? Okay, so now that we have made this clear, we can go ahead into this question. So AC motor behaves as what kind of filter? Not only AC motor, any kind of motor for that matter. You may be aware from your machines course that a motor can be represented as some R and then some L, and then you have some EMF. It's if it's a DC motor, right? So you have your LA or RA, your armature resistance and your armature inductance, right? And you have your back EMF E, and this is your terminal voltage VT or V as you may call it. Okay, so from this you can understand that your armature winding actually presents a finite impedance, that is um, a finite impedance based on RA and LA, right? So ZA is what? RA plus J omega LA. So you can understand that as your frequency increases or omega increases, this term is going to dominate, right? As omega increases, J omega LA more than RA, correct? Which means that your ZA can be approximated as J omega LA. Or if you neglect this J term, ZA is approximately equal to omega times LA, right? So what you see over here, your Z is as omega increases or log F increases, your Z is also going to increase, right? It's going to be something like this. This is not zero, mind you, there is no log zero. Of course, this will go on decreasing. Okay, so you see that as omega increases, log omega increases, your Z is also increasing, correct? Which means that the impedance increases at higher frequencies and the impedance is lower at lower frequencies. Therefore, an AC motor can be approximated as a low pass filter. Got it? So till this point, if you have any doubts, you can go ahead and ask. I will just pause for 2 minutes.
Sir,
Yeah.
can you just explain it again? Fourth one.
This particular question or
Yes, yes, sir. Fourth one only.
okay. Yeah. Just give me a moment. I'm actually setting a lot. I just increase the fan speed. Okay. So one thing is you may be aware of different kinds of filters, right? You have LPF, HPF, and band pass filter, and reject filter, and stuff. Correct? So all of these filters you can actually realize just using analog circuits. Okay, using op-amp circuits or you using LNC. So why do they come about? Because of frequencies. Okay, what is low pass? Which means that it is able to pass lower frequencies and it is able to stop higher frequencies. So that is what is called as low pass. Similarly, what is high pass? It's able to pass allow higher frequencies and reject lower frequencies. Correct? Similarly, band passes, it is able to pass only a range of frequencies, okay, that you may have. Or band reject is the exact opposite. It can just filter out some frequencies or a particular frequency or a range of frequencies. For example, let's say that you want to filter out harmonics, okay? So means that you want, let's say you want only the 50 hertz component to come. You don't want anything else, right? So then you can have a band pass filter saying that, okay, I want range, I want frequencies only between 49 to 51 hertz and reject all other frequencies, right? So all of these can be, I mean, realized using just passive components, using L and C's and R, okay? So based on these, you have a number of configurations. So how you configure these LNCs will actually define which kind of filter it is. Okay. So as you can understand, this LPF, if you draw the frequency characteristic. So what do I mean by frequency characteristic? I have a log F over here and I will have I will have my impedance over here. Mind you, I'm drawing only the magnitude. Okay. That's why I'm writing it something like this. Okay. So low pass, you can understand that I want it to pass low frequencies. Let's say frequency below some arbitrary number, frequency below 1 kilohertz. Okay. And I want to reject all other frequencies, right? So it can have something like the impedance is very low below 1 kilohertz and impedance goes to infinity more than 1 kilohertz, right? So this is actually an example of a low pass filter. Okay. This is something that's not practical. Anyway, I have drawn this to show you an idea. But what you want is at lower frequencies, you want the impedance to be lower, and at higher frequencies, you want the impedance to be high, right? And exactly opposite is a high pass filter, right? So wherein you will have high impedance at low frequencies, and you want it to pass higher frequencies, which means that you will have low impedance at higher frequencies. Okay. So, I mean, these are all ideal characteristics that I'm drawing. This is not practical, mind you. Okay. Similarly, you can have band pass filters as well. So, wherein you will have only within a certain range of frequencies, the impedance will be low. That is, it will be infinite or very high for low frequencies. Then it will suddenly drop to a very low impedance at between a range of frequencies, and then it will again become high. Got it? So this is what is called as a band pass filter. Okay. Similarly, you can also have band reject filter, which means that you will have low frequencies at all other points, and you will just reject a range of frequencies. Right? You got this? Between F min to F max, you will have very high impedance, which means that I am rejecting these frequencies. Okay. So these are all very ideal characteristics. This is not something that's practical. Okay. So now what's actually practical is this, that okay, at low frequencies, you can have low impedance. Okay. Low frequencies, you have low impedance, and as frequency increases, the impedance also increases. Right? So this is an example of a low pass filter. Similarly, similarly, you can have high impedance at low frequencies, and as your frequency increases, my impedance also decreases. Okay. So this is example of a high pass filter. Okay. So from the, before we go to the question, from these itself, you can understand, okay, from the devices that you know. From the devices that you know, you have R, L, and C. So how does R vary with frequency? R does not vary with frequency, it remains R. How does L vary with frequency? It varies as omega L. Z is omega L, right? And C, for C, it's Z is 1 by omega C. Okay. Omega is, of course, 2 pi F, correct? So now that we have made this clear, we will just draw the frequency characteristics of just L, C, and R. Okay. Okay. So Z as R. So it remains R throughout the entire frequency spectrum, right? So what will happen to Z as L? Z is equal to omega L. So as your omega increases, Z also increases, right? So omega increases, Z also increases. Okay. And the other one is Z is equal to 1 by omega C. As your omega increases, Z decreases, correct? Z is 1 by omega C, inversely proportional. So from this, you can understand that, okay, this is independent of frequency. And oh my God, okay, it just got rubbed off. Anyway, I think you got my point that you have something like this, or this is 1 by omega c, and this is omega L. So from this, you can understand this that omega L is something like a low pass filter, correct? Oh, I don't know why it's happening. And it's getting rubbed off. Anyway, so did you understand that this is like omega L and this was like 1 by omega C. Therefore, omega L or L is actually a low pass filter. Your inductance is something like a low pass filter. Got this much? Till this point, is it fine?
Yes, sir. Got on.
Now, now the point is, question is about motors. Okay. So your motor is, well, what does a motor have? Motor has what is called as an armature winding, right? It's a winding. So as you can understand, if you have something, I mean, coiled around the frame, a magnetic frame in this case, obviously you're going to have some inductance, L, right? Because what is L? L is actually nu n square A over L, where L is the length and A is your area of cross section and nu is the magnetic core permeability, right? So this LA will be actually very, very large for a motor, millihenries, okay? Millihenries is actually large for an inductance. So you will see that this RA will be very small because it's essentially a copper wire. So you don't expect to see much of a resistance in copper, right? So because of that, you understand that the motor actually behaves like an inductance. Okay. We saw that inductance characteristic is something like this. As your frequency increases, impedance also increases. So because of that, at low frequencies, it presents low and low impedance. That is why it passes low frequencies, allows low frequencies, and blocks higher frequencies. Okay. That's why I'm calling AC motor as a low pass filter. Got till this point? Okay.
Sir, sir.
Okay. So we can go ahead to the next. A transistor is connected in parallel with a diode in reverse mode. It has capability of dash. Okay, we will just draw this. I think this is pretty simple. So you have a transistor. They have not told whether it's MOSFET or BJT. I'm taking a BJT. Okay. And you have a diode in reverse. So you should be able to tell this. So one thing is, for such kind of questions, you draw the VI curves. Okay. This is your V and this is your I. This is minus I, minus V. So first things first, can it block voltage in the forward direction? So if I apply voltage over here, right? So can it block positive voltage? Yes, it can block positive voltage because unless I bias this transistor is not going to conduct, right? Which means that it can block positive voltage. Okay. So it can block positive voltage, right? And then can it conduct current in the positive direction? Yes, it can conduct current in the positive direction because if I give some IB, as I told, your IC, your IC is beta times IB. So if I give a positive IB, there is going to be a positive IC, right? That's going to flow over here. Therefore, it can conduct positive current. And then, can it block voltage in the reverse direction? No, it can't block voltage in the reverse direction because if you give voltage in the reverse direction, this diode is going to be forward biased and this diode will conduct. Okay. So you see that it conducts current in the negative direction, but cannot block voltage in the negative direction. It cannot block voltage in the negative direction, but it conducts current in the negative direction. Therefore, it has bidirectional current conduction and only forward voltage blocking. Okay. And you will see that instead of BJT, if you use a MOSFET, it turns out to be the same. Okay. So this is fine, good enough. We'll go to the next. Which of the following has bipolar voltage withstand capability? Bipolar voltage withstand capability, as in like it should be able to do both of these, right? So that's the point. ACR, GTO, ACR and GTO both, none of these. Okay. So this is your ACR. Okay. And to be exact, this is the symbol for ACR, and for GTO you have something like, right? So gate turn off is also controllable. Anyway, the question is which has bipolar voltage withstand capability. So this ACR, it can conduct current in the positive direction. Therefore, this is true because if you supply a current, gate current, which is more than IL, your latching current, it's going to start conducting in the positive direction. And of course, it can block voltage in the positive direction if your gate current is lesser than your latching current. Correct? It's not going to turn on simply. Therefore, positive voltage conduction is also positive and possible, and reverse voltage blocking is also possible. Correct? Okay. So ACR obviously has bipolar withstand capability. What about your GTO? In your GTO, only difference from ACR and GTO is, as you know, the turn off is also controllable. Whereas in ACR, the turn off is not controllable. That's why we call it a semi-control device. Okay. As far as turn on is concerned, both of them are quite similar in their operation, right? So voltage withstand capability, as far as voltage withstand capability is concerned, both of them can block positive as well as negative voltages because they simply refuse to turn on unless your gate current exceeds this latching current. Okay, this is the criteria for it to turn on. And of course, your this should be positive. Therefore, um, bipolar voltage withstand capability is possible with both ACR and GTO. Therefore, this is your correct answer. Okay. What's the relation between breakdown voltage and drift region of a power diode? Okay. So in a normal PN diode, you have your P and then N, A and then K. You simply apply a positive voltage more than 0.7 volts and this starts conducting. This is actually an analog diode or a signal level diode. In a power diode, you have E and then an N minus layer and then an N plus layer. You have an N minus layer and then an N plus layer. Okay. So due to which this N minus layer is actually called as the drift layer. If you make this wider and wider, your voltage blocking is going to increase if you make this wider and wider. Okay. So let's say you want 300 volts blocking and 600 volts blocking. The only difference will be this N minus region. If your N minus region is bigger, you can have higher and higher blocking voltages. Okay. So the answer is directly proportional. Breakdown voltage and drift region, both of these are directly proportional. Okay. And this N minus drift region is something seen not only in power diode, in case of power MOSFET or BJTs and stuff like that. You will have in the market, you will see power MOSFETs rated for 650 volts, power MOSFETs rated for 900 volts, 1.2 kVs, even 1.7 kV power MOSFETs have come about. Okay. So what's the difference? The point is width of this N minus region. So 650, 900, 1.2 kV. All of these are MOSFETs, right? The only difference is due to this N minus region. Okay. The wider your N minus region, more will be the voltage blocking capability. Okay. But on the downside, the wider your N minus region, right, your channel resistance, the resistance increases. Okay. If your resistance increases during the on state, you want the resistance to be as low as possible, the resistance of the switch to be as low as possible. But if your resistance increases, the losses also increase. Okay. So just because, let's say your application requires 250 volts, it's not necessary to use 1.2 kV MOSFET. You can use 650 volt MOSFET. The reason is, if you use 1.2 kV MOSFET, it's nothing wrong. The point is your R is going to increase, which means your losses are also going to increase. Why is the R increasing? It is because your N minus region is larger. Larger your N minus region, more will be the resistance. Okay. But anyway, as far as this question is concerned, breakdown voltage and drift region, they are directly proportional. Okay. So this is a very, very simple question. Fast recovery diodes are used in what applications? And reverse recovery of these is dash. Second question is pretty simple. Fast recovery diode, as you can understand, they are very fast, which means that reverse recovery time is TRR. This is very small, right? Right. So this is your TRR, and your TRR is actually very small. So it can be either of this or these. So fast, because your TRR is very small, your frequency can be higher, right? Because the time expended is very small, so you can turn on and turn off this diode very fast, right? Which means that you can increase your frequency. So the answer is D. Okay. Okay. So the reverse blocking capability of Schottky diode compared to power diode is what? So we have seen this a number of times. So you have your P and then in a normal power diode. In a Schottky diode, you have a metal over here and then you have the N region. As I told, in a metal, your valence band and conduction band are actually overlapping. So let's say this is your conduction band and this is your valence band. So your valence, oh my God, this is your valence and this is your conduction. Both of these are overlapping. Okay. In over here in a semiconductor, you will see that conduction band and valence band are actually distinct. So conduction band will start only from here and valence band is only till this point. So you need to cross this potential, barrier potential, it will be some electron volts. In a metal, this is not there. Both of these are overlapping, right? So as you can understand, its voltage blocking capability will be lesser because metal cannot block any voltage. It is ready to start conducting, right? So the only bulk of voltage blocking is done by the semiconductor region over here. Because you have two regions over here, semiconductor regions, its voltage blocking capability will be way higher compared to a Schottky diode. Got it? So that is why the reverse blocking capability of Schottky diode is actually very low. It cannot block voltage. Why? Because of this metal. Metal cannot block voltage, it will start conducting. So which of the following device has controlled turn on and uncontrolled turn off? SCR diode, IGBT, MOSFET, and track. Okay. So this is pretty simple. The answer is SCR. Why? Diode uncontrolled, right? It will start conducting as soon as you apply a positive voltage over here. And you may be aware of IGBTs. In an IGBT, you have your collector, emitter, and then gate, right? If you apply a positive VGE, IC flows. And as soon as you remove this VGE or you make VGE negative, IC stops, right? So it is fully controlled. So this is fully controlled. So your IGBT is fully controlled. So if your VG is positive, IC will go. If your VG is negative, IC will not flow. Similarly, your MOSFET. MOSFET is also something similar to this, right? So in a MOSFET, we will of course know this is your ID and this is your VGS. If your VGS is positive, ID will flow. And if your VGS is less than the threshold, your ID will not flow. So this is also fully controlled. Okay. Both of these are fully controlled. Okay. And triac, as you know, is a 4-quadrant device. Okay. It is capable of voltage blocking, voltage conducting, and it is also fully controlled. Okay. So only thing is SCR. So wherein your SCR, your turn on is controlled. Why? You can control the gate current. Only if you apply IG more than I latching, the SCR turns on. Okay. However, if you make your IG less than I latching, the ACR will not turn off. In order to turn off the ACR, you need to apply sufficient negative bias voltage. Also make sure IG falls less than I holding current. There is something called the holding current. Only if you make your IG less than I holding current and also apply a negative voltage, the ACR turns off. So turn off is not that simple in an ACR. Therefore, it has controlled turn on and uncontrolled turn off. Okay. So before we move ahead, anyone has any doubts till this point? Uh, so first thing, am I audible?
Yes, sir.
Okay, good. Um, just give me 2 minutes. I'll just have some water. My throat is actually really bad. Meanwhile, if you have any doubts, you can go ahead and ask your questions till this point.
No, sir.
Okay, good. Just give me 2 minutes. I'll have some.
Okay, sir. Please take care.
Okay. So we will resume. So the next question is, RDS on has a dash temperature coefficient, whether it's positive or negative, or can it be both, or is it totally independent of the temperature? Okay, so what's this RDS on? Right? As you can understand, this is for a MOSFET because you have RDS on, that is where D is your drain and S is your source. So if you see the operation of the MOSFET, ID or I channel, as I will call it. Okay, so there's a representation of a MOSFET, and as we saw earlier in the first question, MOSFET is a voltage controlled current source. VGS controls your I channel. Okay, and if you saw your, if you see your VI characteristic, you have your V and then I, where this is your VDS actually, and this is your ID or I channel. Okay, so if you see your VA characteristic, it's going to be, okay, so this is for increasing values of VGS. And as I told, the slope over here, you can assume this to be fairly linear. The slope over here is what? Delta ID by delta VDS. This is going to be 1 by R. So this is actually called as your RDS on the slope of ID by VDS. So if you change your VDS, the change in ID and change in VDS, if they are linear, right? If they are proportional, then the constant of proportionality is called the RDS on. Physically, if you see, as you can understand, you can categorize the operation into three regions, right? You have your ohmic region, you have your cutoff region, and then you have your saturation region. So what's your saturation region? The I channel or your ID refuses to increase beyond a certain value of VDS, right? It remains constant. Okay. So you can understand that it can be in the ohmic region or it can be in the saturation region, right? So if it is in the ohmic region, as you can understand, the MOSFET presents a constant resistance, and this is what is called as RDS on. Okay, and if it's in the saturation region, you see that it's a constant current, right? The current is constant. It has saturated. Okay, so current is constant, which means that the MOSFET now acts as a current source. Why? Because the current is constant. As I told earlier, this current source is equal to Gm into VGS minus V threshold. So based on the value of VGS, this constant current source value also varies. That see over observe carefully that I'm using this symbol to represent a current source. Normally we use this, right? This is an independent current source. Over here, this is a dependent current source. Why? This current value is dependent on VGS. That's why I'm using this kind of symbol, a kind of symbol made of lines. Anyway, so you have two representations based on whether it's in the ohmic region or saturation region. Okay. So now coming to the question is RDS on. This RDS on, is it dependent on temperature? If it is dependent on temperature, how is it dependent? If it's a function of temperature, how is it dependent? So will this RDS vary with temperature? Will it increase? Will it decrease or what? Okay. So to answer this question, I will not be going into device physics and stuff. But anyway, if you go to data sheet, so that is what we require as a power electronic engineer. We are entirely dependent on data sheets. Okay. Device data sheets, because As far as a device is concerned, we treat it as a black box with, we know the input and we know the output, and we just want to know how the box is going to behave. Okay. So over here, how does it vary with temperature? If you go to the device data sheet, in all the MOSFET data sheets, they will give you a graph of TJ versus RDS. Okay. They will give this graph, how temperature affects your RDS, where TJ is called the junction temperature of the device. Okay. Anyway, so I'm not going into what is TJ and and stuff, but anyway, this is the device temperature and this is your RDS on. You will see that it has a curve something like this. Okay, as your TJ increases, your RDS on increases. Okay, so at higher values of TJ, you will see that RDS also increases. So the answer for this question is RDS has a positive temperature coefficient. Okay. RDS has a positive temperature coefficient. There is a reason I have written predominantly in this question. Okay. So as I told earlier, you have number of semiconductor technologies, SiC, silicon carbide, gallium nitride and stuff. Okay. So for gallium nitride, you will see something like this. Okay. Let's say this is from -25 to 150 degrees Celsius, and you will see that it's entirely increasing. For silicon carbide, there is something interesting that's going on. Until around 20 degrees, you will see that it has a very small negative slope and then it starts increasing. Okay. So this is the reason I have written predominantly. Okay. In general, if someone asks you, okay, how RDS on varies with temperature, it is always positive. But you understand that for SiCs, you will see a very, very small negative temperature coefficient. And then beyond 20 degrees, it will start increasing. So this is for, let's say, -40 to 20 degrees. We generally don't operate the converter between these temperature ranges. I mean, you seldom see a converter operating at -10 degrees or 0 degrees. Okay. Generally, the converter operates at 80 degrees or 90 degrees, something like that, in which you can definitely tell that it has a positive temperature coefficient. Okay. So, in essence, RDS on has a positive temperature coefficient. Okay. Okay. So the next question. BJTs are dash controlled, whereas MOSFETs are dash controlled. So again, it comes back to the same question. VCCS, VCVS, CCCS, CCCS. I mean CCVS. So BJTs. So what controls your IC? What controls your IC is your IB, right? So IC is beta times IB. This is your defining equation, right? So if you have a positive gate current, right, then your BJT is going to get forward bias or it's going to start conducting, which means that your BJT is actually a current controlled current source. Okay. So BJT is a current control device. What about your MOSFET? This is your ID, right? As I told earlier, I channel is GM into VGS minus VTH. If VGS is more than VTH, right? If VGS is more than VTH, then I channel is going to be positive, right? So your MOSFET will start conducting if your VGS is more than V threshold. Okay. And of course, your VDS is positive. Okay. So your MOSFET is actually a voltage controlled voltage controlled current source, right? It's a current source because there is going to be some ID over here. And we saw earlier also, MOSFET can be represented as resistance or it can be a current source, right? So this is what I was telling, voltage controlled current source, and this is the equation. So MOSFET is a voltage controlled device. Okay. I don't think you will be having any doubts over here by now because we have seen ample amount of definitions of whether it's a current source or voltage source and how do we classify them. Okay. So this is something we have again seen in a GTO, the turn off is dash, whereas in an SCR, the turn off is dash. Okay. So as I told, SCR turn on is controlled, right? In both SCR and GTO, the turn on is controlled. How? When will it turn on? If you have a positive VAK and your IG is more than IL, latching current, then the device is going to turn on. Okay. However, if you come to turn off, so how does the device turn off? So to turn off the device, one thing is you need to apply a negative voltage. Also, you need to reduce your IG below the holding current. Okay. So the turn off is not simple in an SCR. You need to do both of these to turn off the SCR. That is, you need to reduce your IG below IH and your VAK should also be negative. Okay. So the turn off is not controllable in an SCR. Okay. It's uncontrolled. Okay. However, GTO was actually invented to get rid of this particular drawback of SCRs. Okay. So in GTOs, sorry. Um, okay. So GTO, the turn off is controlled. In SCR, the turn off is uncontrolled. Okay. Okay. So thyristor is a generic name for a semiconductor switch having number of layers, 2 or more, 3 or more, 4 or more, or what? Okay, so the name thyristor comes only if a device has 4 or more layers of PN and stuff. Okay, so as I told earlier, diode has 2 layers, P, N. Okay, I'm not counting the drift region. Drift region is added just to make the increase the voltage blocking capability. But anyway, the semiconductor physics is governed by only these P and N regions. In a transistor, you can have BJTs or MOSFETs. All of these are three, they have 3 layers, right? So it can have NPN or PNP, BJTs, or in MOSFETs also have N channel or P channel. Okay. But if you see the physical stack up, they will have 3 layers. The thyristor nomenclature is for 4-layer devices. Okay. 4 or more. 4 or more. Okay. So ACRs, triacs, GTOs, MCTs, then diacs, all of these have 4 or more layers in them. Okay. So that's why you have the name thyristors. And true to this, more than 4 layers, you will see that ACRs, the rating of ACRs is, it can be more than 1 kV. Okay. MOSFETs, maximum you have up to 1.2 kVs. Okay. Maximum commercially. But ACRs, you can have 6 kV ACRs. Okay, not a problem. That's why you will see ACRs being used in the generation or transmission or distribution side. Okay, MOSFETs are used for uh, up to high power applications. You may tell up to a few hundreds of kilowatt. However, ACRs you can very well safely employ them for few megawatts. How? Because They are rated for very large voltages and currents in order of kiloamps, okay, and kilovolts. Why? The reason is basically they have large number of layers. Okay. Okay. Which of the following is true about IGBTs? Input carry. Okay. So what is IGBT? Insulated. I'm sure you are aware of these, but anyway, insulated gate. That means the gate is insulated. Bipolar transistor. Okay. So it's a transistor, which means it's a 3-layer device. Okay. Bipolar, right? It means it can conduct current in both directions. And of course, you can apply voltage in both directions, but we need to see whether it can block that voltage or not. And main thing is insulated gate. So why this came about? So we will go into a bit of history to understand why this came about. Okay. So you know your conventional BJTs, right? So you have your IB and your IC. As you can understand, there is no insulation over here. So this um, you will have some base resistance and some emitter resistance RE. You will apply a positive voltage over here. Let me call this VB. So your loop is something like VB is equal to IBRB plus you will have some drop VBE plus VBE plus IERE, right? So all of you are well aware of this, right? So what is IE? IE is IC plus IB. What is IC? It is beta times IB plus IB. So that is 1 plus beta times IB is your IE. Okay. Anyway, the point is, and this VBE may be some points on volts again. The point is that it's not isolated, correct? So this IB flows over here and you have an IE which is a consequence of this IB. It is non-isolated. And you of course understand there is a major drawback of BJTs. What's the major drawback? You always need a positive current. IB needs to be continuous positive current. Okay. You need a positive current, which means that for the entire duration of this BJT being on, for the BJT to be turned on, you need a continuous IB. Okay. Which is not good because if you have current, it means that you're going to have I square R loss. Right? Not only that, the device is going to heat up if you have continuous current. So what we want is something like, okay, you can have positive voltage, but you don't want to have continuous current. You can have a continuous voltage, okay? So let's say you give plus 5 volts or plus 6 volts. Doesn't matter if you are not going to flow continuous current, okay? So this is a drawback of BJTs in the sense that you need a continuous current to keep them forward biased. Sure. Okay, but the good thing about them is you have your IC, which is proportional to beta times IB, which means that if I control this base current, I also control what is IC. Okay. Okay. So this is one. The other category in transistors is, of course, MOSFETs. In MOSFETs, as we saw earlier as well, you don't need a continuous current. You don't need a continuous base current, or you don't need a continuous gate current. Correct? You only need a positive voltage. VGS. So drain. You only need a positive voltage. If your VGS is more than V threshold, that is enough to keep the um, device forward biased, right? You don't need a continuous gate current. IG need not be continuous, need not be continuous. So that's one good thing about MOSFETs. Okay, so you don't need to continuously supply a gate current. Okay, by nature, you can easily get voltage sources. It's difficult to get current sources. So you now understand, right? Like it's easier to connect just a voltage source. You connect a battery, right? and that's going to take care. It will maintain a positive voltage over here. Plus 15 volts is the typical requirement of a MOSFET. So it can maintain plus 15 volts. Okay. But it cannot, I mean, it's difficult to find a source that will continuously give you a constant current of IB. Okay. So the advantage you get over here is you don't need a continuous gate current. You just need to have a positive voltage over here. But the disadvantage is if you have a constant VGS, ID is what? GM into VGS minus V threshold. So for a fixed VGS, your ID is also fixed. Okay. So you don't have much of a control over ID if your VGS is fixed, right? So the idea is you want to have the conduction characteristics of BJT. Okay. Conduction characteristic of BJT, but biasing characteristic of MOSFET. Till this point, you have any doubt in this question? You want a conduction characteristic of BJT and you want a biasing characteristic of MOSFET. Okay, why biasing characteristic of MOSFET? In a MOSFET, it's voltage control. You just need to maintain a voltage. You need not supply continuous current. In a BJT, that's not the case. You need to supply a continuous current, right? Yeah. So ideally, what you want in a transistor is you want a conduction characteristic of BJT and a biasing characteristic of MOSFET. Okay. And this is also true in a MOSFET that see, unlike BJT, it is the gate is totally isolated. That's why we have two lines over here. It's totally isolated, right? The gate is not directly connected to the drain of source. Okay. Sure. The connection is only through some parasitic capacitances. It's not a direct short. That is why you cannot write IG is equal to ID plus IS or something like that. Okay. In BJTs, you were able to write IC or IE as a summation of IB plus IC, right? So in BJTs, you were able to write that IE is equal to IC plus IB. In This is true. In MOSFETs, you cannot write IS is equal to ID plus IG. This is totally not true. Okay, the reason is it is isolated. The gate, drain, and source are isolated. So you want this isolated characteristic, right? So this is something that you get with MOSFETs, but you want the conduction characteristic of BJT. So with this idea or motivation, a person came up with IGBTs. So this is how IGBTs were invented. Okay. So just as an extra piece of information, it is actually really good or worth mentioning that the person who came up with this idea is actually an Indian. Okay, and he is an expert in device physics. So he is actually Professor Jayant Baliga. Okay, he is in I guess North Carolina State University in US, but I'm not exactly sure. But he's the person who came up with this idea. Okay, to have what is called as something like this, right? So you have a MOSFET characteristic of gate and emitter and then collector. So you have a MOSFET characteristic in the biasing side, but you have a BJT characteristic in the conduction. Okay, so you have an IC, but you need to apply only a positive VGE. This is something that's great, right? Like you are able to get MOSFET characteristic in the bias side, but get BJT characteristic in the conduction side. So that is why you will see that this IGBT, that is why it's called an IGBT, insulated gate. The gate is insulated, right? And it's a bipolar transistor, similar to BJTs. That's something really great. Okay. So that is why you will see that IGBTs, they are typically rated for very high voltages, again in the order of kVs, and again of the order of kiloamps. But at the same time, it's easily controllable. Okay, you can control VGE, and the conduction is also controlled. And if you withdraw VGE again, it turns off. It doesn't need a continuous gate current. right? So this is something that's really helpful, right? And if you actually connect an anti-parallel diode, you get the characteristic similar to a MOSFET. Okay. So, okay, anyway, coming back to the question, which of the following is true about IGBTs? So now that I have told this much introduction, you should be able to tell that the input characteristic is the biasing characteristic, right? Biasing characteristic is similar to a MOSFET. The output characteristic or the conduction characteristic is similar to a BJT. So the option is D. Input characteristic similar to MOSFET, output characteristic similar to BJT. Okay. So there's actually a very good question. So it's good that I was able to discuss this with you guys. Okay. So it gives you an understanding of how the devices came about, right? Like it's not someday that they just thought of IGBTs. Okay, so let's make IGBTs. It's that it involved a lot of thought processes to how they came about with IGBTs. Okay. Okay. So yeah. So the next question is, this is actually a good question. Interesting. How many modes are possible with a given switch configuration? Modes as in like you have your V and then your I minus V minus I. Okay. So first things first, apply a positive voltage and see if it can block positive voltage. So can it block positive? Okay. So this is an SCR and this is just a diode, right? Okay. So can it block positive voltage? Yes, it can block positive voltage because unless you supply a positive gate current more than latching current, this will not conduct, right? And of course, diode cannot conduct in the positive direction. So yes, this switch can actually block positive voltage, right? So can it conduct current in the positive direction? Yes, it can conduct current in the positive direction if this SCR gets forward biased. And if you give IG more than IL, this can conduct current in the positive direction. Excuse me. Okay, so can it block reverse voltage? So you may tell that this SCR can block reverse voltage, but this diode absolutely cannot block reverse voltage, right? So if you give a voltage something like this, for this diode, this is a positive voltage. This diode is instantaneously going to start conducting, which means that it can conduct current in the negative direction, but cannot block negative voltage, right? So bidirectional current capability and unidirectional voltage blocking, right? Bidirectional current, bidirectional voltage. Okay. So how many modes? One, two, three. So three modes are possible. Okay. So in a similar vein, we can also see another example. How many modes are possible? So this is just an addition to the previous question that, okay, I now have a series diode with the SCR. So I have SCR, diode, diode. Okay, you may feel that, okay, what's the difference? Anyway, this diode is an um, uncontrollable device. So does it have any impact? Let's find out. Okay. This is the last question. So after this, we can wrap up the session. I will open the floor for any doubts anyway in the after this. But anyway, this is the last question. So first things first, can it block positive voltage? Yes, it can block positive voltage because if you apply a positive voltage over here, this is your anode and cathode. Okay. So if you apply positive voltage and if you make only if Ig more than IL, this ACR is going to conduct, or else this ACR will not conduct, right? So it can block positive voltage. Can it conduct current in the positive direction? Yes, it can conduct current in the positive direction if your Ig is more than IR, and if you have a positive voltage, this diode will anyway be forward biased. So it can conduct current in the positive direction. So can it block negative voltage? No, it cannot block negative voltage because the diode is getting ready to get forward biased. So it cannot block negative voltage, and it can conduct current in the reverse direction because this diode will turn on. Okay, so again, it has three modes. So this is just I mean, these are just two examples. You can, of course, have multiple combination of switches and you can try to find out their conducting quadrants, but the test is simple. Just apply positive voltage and see whether it can conduct current and block that voltage. And of course, again, apply a negative voltage and see whether it can conduct negative current and block negative voltage. And that's it. Okay, you can just see where it fits in this VI curve. Okay. Of course, people give names such as for these VI curves, people have names like forward, blocking, forward. Okay, so this is actually called, so this is called forward conduction. So this is called reverse blocking. So this is called the reverse conduction. Of course, people can ask you, okay, is forward blocking possible, forward conduction possible, reverse blocking possible, and reverse conduction possible? Okay. So anyway, so all of these fit into the same envelope. That is, just have your VI curves. Just have your VI curves and categorize where it fits in, right? So forward blocking, forward conduction, reverse blocking, reverse conduction. Simple. Okay. So I think I'm done with this. Yeah, I'm done. So till this point, if you have any doubts, you can go ahead and ask, right? And after this, we can conclude. Yeah, so please go ahead if you have any doubts. Or if you want me to repeat anything, or if you didn't understand anything, you can go ahead and ask. Okay, so just a second. Okay, so I can't understand the device characteristics. Once again, please explain. Yeah, sure, I will explain that. Could you please clarify how minority and majority and minority device carrier devices are classified? Okay, so um, yeah. So one thing is this majority and minority carriers, it goes a bit into device physics. So actually, I didn't want to touch upon that. That's why I didn't go inside that one. But for practical purposes, mm, empirically, we can actually understand how they are useful in the field of power electronics, but I really don't want to go into how they are classified, okay? Because they are actually not required. And as a power electronics person, even I'm not exactly that sure as to how people come about with whether they are minority and majority carriers. We just know that, okay, MOSFETs are majority carriers and, diodes are minority carriers, okay? Anyway, but let me go into this particular question, that how the conduction modes are classified. So we might have studied VI curves for all devices, right? So for example, you might have studied that for diodes, you have something like this, correct? This is your 0.7 volts, right? And in the reverse direction, you have something like this, correct? How you have an avalanche breakdown over here, and yeah. Similarly, you have for MOSFETs or BJTs, you have something like this, right? So this is for increasing value of VGS or increasing value of IB, right? So this is your VDS or VCE in case of BJTs, and this can be your ID or IC in case of BJT. So ID for MOSFET, drain current, or IC for collector current in a BJT. Okay. Anyway, this is again your VI curve, right? This is VD and this ID. So from this curve, what you understand? You understand that, okay, so it is capable of blocking voltage in the positive direction, and it is also capable of conducting current in the positive direction. Correct? This is what you understand, right? So you are able to give a positive voltage and you are able to see that it conducts current. And at the same time, you are able to infer that even if you give a positive voltage, there is a possibility that the device will not conduct. There is a possibility of a cutoff region, right? The device will not conduct until your VGS exceeds V threshold. Until your VGS exceeds V threshold, the device will not conduct, right? It means that voltage blocking is possible. Okay, you may give 400 volts, but until your VGS does not exceed the threshold voltage, the device is not going to conduct. Okay, so voltage blocking is possible. And of course, forward current conduction is also possible, right? The device is ready to conduct current. If you give VGS more than V threshold, this is the controlling factor. So this is what we call as forward voltage blocking. Okay. And this is what we call as forward current conduction, FC and FB. Okay. I mean, you can call it forward conduction, forward blocking, or something like that. So similar, I mean, true to that only, we have something called as forward blocking and forward conduction. This is fine. So now that we have this, we can also have something of the opposite kind. That is, we have something called as reverse blocking and reverse conduction. That is, for example, take this diode, right? So you are seeing that, okay, beyond a particular voltage, the device actually cannot go on blocking infinite voltage, right? It starts uh, to have an avalanche breakdown. But ideally, you don't want this breakdown, right? Ideally, you don't want the device to break down. If the device undergoes avalanche breakdown, that means that the device has failed, right? So ideally, you want that the diode goes on blocking this much, right? Okay. So the point is, there can be a reverse blocking capability of a device, and there can also be reverse conduction capability. For example, take this case, MOSFET, right? So the presence of this antiparallel diode indicates that it can conduct current from source to drain, right? Through this MOSFET, which means that reverse conduction is possible, right? In a MOSFET, reverse conduction is possible. So this is possible, right? Whereas if you apply reverse voltage, can it block reverse voltage? It cannot block reverse voltage because the moment you apply reverse voltage, this MOSFET says I am ready to conduct, right? So this is not possible. Reverse voltage blocking is not possible, right? Because this MOSFET turns on. Reverse conduction is possible. Okay, and of course, forward blocking is possible and forward conduction is also possible. Why? Forward blocking is possible when if you apply, as I told, if you apply, let's say, high value of VDS also, doesn't matter if you apply 650 volts. Only if your VGS greater than V threshold, it will conduct, right? So forward blocking is possible. It can block 650 volts and it can conduct current if you apply VGS more than V threshold, right? So these are the modes of conduction. And for SCR, right? This is the device that's remaining. SCR, right? So what is the criteria? And of course, your VAK should be positive, anode to cathode, and your IG should be more than IL, right? So you understand that if your IG is less than IL, it can go on blocking a positive voltage also, right? So forward blocking is possible. Okay. And forward conduction is also possible. Why? If the device turns on, the current flows over here, right? Forward conduction. So forward conduction is possible. And of course, it can block a reverse voltage, right? This ACR cannot conduct like this, right? This is impossible. So this is impossible, whereas it can block a reverse voltage. This is possible. So reverse blocking is possible. Okay. So this is for a single switch. For a single switch, this is possible. Okay. For a single switch, this is possible. Single MOSFET, this is possible. Single ACR, this is possible. Okay. So you get my point, right? So you have multiple operating quadrants of a switch. Okay. So you can be in this quadrant and this quadrant in an ACR. You can operate in these two. I mean, you can operate in these two quadrants for a MOSFET. Okay. I mean, in for a diode, you only have one quadrant of operation. Okay. So the idea is you can have multiple modes of operation or multiple quadrants of operation of a device. Okay. The questions till this point, is it okay? Right? It is okay, right? If you have any doubts, you can of course comment once again. But the questions we saw over here where we try to realize switches that can, that can maybe move away from different modes. Okay. As I told, if you just take the SCR was capable of bidirectional voltage blocking and unidirectional current conduction. Correct? SCR was capable of this because SCR can block reverse voltage and it can conduct current in one direction. Now what I did was I just connected an anti-parallel diode. What happened if I apply a reverse voltage, this SCR may block the reverse voltage, but the diode cannot block this voltage, right? For the diode, this is a positive voltage that's appearing over here. Okay, so the diode will start conducting. So that is why the diode conducted something like this, right? So as far as this device is concerned, reverse conduction is possible. Okay, that's why this is possible. And of course, this is also possible. So this is also possible. So forward conduction is possible. Reverse conduction is possible. Reverse blocking is not possible. And forward blocking is possible. Why? If I apply positive voltage over here and make sure that if my IG is less than IL, this SCR will not turn on, right? So if I apply a positive voltage and make sure that IG less than IL, the SCR doesn't turn on at all. So it can block positive voltage. So this is also possible. So what are possible? So what are possible? Forward conduction, forward blocking, and reverse conduction are possible, which means three modes are possible. Got it? So this is how we did. So now you understand, right? Like you can emulate, this is a characteristic we saw for MOSFETs, right? Generally, a MOSFET has these characteristics, correct? That is forward conduction, forward blocking, and reverse conduction. Now you realize that, okay, in case you are an engineer, right? So most probably while working, you will be seeing that you don't have all the resources available at hand. So with the available resources, you will try to make impossible also possible, right? So if you want to realize realize the operation of a MOSFET only using SCR, right? This is something you can do. Okay, just connect an SCR and diode, something like this. You can emulate a MOSFET. Got it? So I think this should give you a perspective. This is just a starting step. Okay, so right, you have an SCR and you have a diode, and lo and behold, you move away from an SCR and you get into the operation of a MOSFET, something like this. MOSFET operates in these three modes, right? It can have forward conduction, forward blocking, and reverse conduction. Okay, so I think this is amply clear, right? So you using SCR and diode, we realize MOSFETs, right? Okay. So anything else? Okay, for SCR has only two quadrant operation in first and second quadrant. MOSFET quadrant 1 and 4. Body diode is inherently present only in MOSFET, sir, or other devices. Okay. MOSFET is body diode is inherently present in MOSFET. That is true. It is due to the devices. If you go through the device's lateral structure, you will see that a PN junction is formed in the reverse. Okay, in the structure, lateral structure of the device itself. So body diode is inherently present. Okay. In any other device, it's not present. For IGBTs, you know, right? Like as I told, IGBT, the conduction is emulating a BJT, whereas the gate drive is emulating a MOSFET. Okay. So over here, what they have, what they do is they externally add a diode. Okay, they externally add a diode so that you get this reverse conduction capability as well in an IGBT. Okay. So in an IGBT, they externally add MOSFET. Okay, in an anti-parallel fashion. I'm sorry, they externally add a body diode in an anti-parallel fashion so that you are able to emulate reverse conduction as well. Because IGBTs you may be using in applications where reverse conduction is required also. For some time, reverse conduction is also required. So if you see all commercial IGBTs, most of them have a body diode in anti-parallel. Okay. So SCR has only two quadrant operation in first and second quadrant. MOSFET 1 and 4th quadrant. Yes, you are right. So this is the point. So SCR has bidirectional voltage blocking and unidirectional current conduction. And MOSFET has bidirectional current conduction and unidirectional voltage blocking. So yeah, you are right in that. Okay, thanks. So I presume you don't have any other doubts, so I can end the session, right? Okay, so I will stop recording and we will be done with the session. I hope you were able to um, hope you were able to